Hello.
Focusing on from now.
So, good morning. Today,
You do whatever you want.
essentially talking about an adventure in science, which is in quest of the theory of everything. And what does the theory of everything mean? So, basically, we'll talk about finding a theory that describes all physical phenomena in one equation of sorts. Yeah. And many scientists have embarked upon this. And speaking of scientists, let's start with one of the most renowned ones. That is the Apple guy, not Steve Jobs, but Einstein, Newton. And Newton started with his work in the laws of motion, and we studied him in 8th grade in a subject called physics. And he is very famous for his gravitation law, which he published in 1687 in Principia. So he gave the equation, and at the 17th century, this equation was very famous. As for people, it was marvelous. It was like one body in space affecting somewhere else, and Newton gave an equation for that, and it actually worked. So if you plug in the numbers for the mass of the Earth, your mass and stuff, it actually gave you 9.8, and which was very shocking to the audience then. So it was a great thing at that time. But we see that he made a mistake, and Einstein corrected this. So the mistake he made was that he took space and time to be absolute, which basically means that Einstein thought that in his theories of relativity, that space and time is relative to different observers going at different speeds, etc. But he took it to be absolute. Like in our day-to-day thinking, it's obvious that here, there, space-time will be the same. But at cosmic levels, it's a bit different. That's what Einstein corrected. And if you think about it, he just gave the equation, how to calculate it, and calculate the force. He didn't explain why it was there, why it existed in the first place. So, yeah. Later comes Einstein. He corrects his work. So, Einstein redefined Newtonian gravitation, and he becomes famous around the 1920s. So, and he essentially, what Newton didn't explain was why gravity was there in the first place. So that's what he did. He explained why gravity was there using his theories of relativity, special and general. So one of these, general relativity, is one of the pillars of 20th century physics, and the other pillar is quantum field theory, which we'll talk about. So let's start with general relativity. So by pillars, we mean that in 20th century physics, all of their thinking depended on general relativity and quantum field theory. There were two main things. And general relativity, as I said, essentially we defined Newton's law of gravitation. And it described, it worked with gravity. And Einstein, as he thought of space and time to bend, what do we mean by bend? That's what he thought. So that was his imagination of what happened. And he said that gravity exists due to this bend in space-time. Yeah.
Fine. So as Kian mentioned, there are two pillars of physics, right? So I'll be talking about the second pillar, and that is quantum field theory. So while quantum field theory is basically the physics of very small stuff. So at the turn of the 20th century, what people found was that the atom isn't, the most fundamental unit of everything. There was something more, like they found electrons, they found protons and neutrons. And even that idea that, these three particles were the most fundamental things was also found wrong. We found even more, we went deeper and we found new particles in these particle accelerators that, basically atoms and protons are like smashed together. And one of the things quantum field theory predicts is that particles, they exist in this sort of field. So, like, there are forces, right? And they create some certain field. So particles then interact with the field, and have certain effects. So you could think of it like if something's moving and interacts with the field, then it exerts some force, of some sort. And the other thing that quantum field theory predicts was the standard model of physics. Now, the standard model is essentially like a periodic table for particles. And it's like a table which, just puts every fundamental thing together. So you can see that there are two categories, fermions and bosons. So fermions are your actual matter. They're like your actual building blocks. So that's the electron, this up quark and down quark, together they make up the protons and neutrons, And the other particles, all these other things, other fermions, they're much heavier versions of these three, and they're more unstable, so we don't really see them in a regular environment. They just decay into these lighter versions, the electrons, quark and down quark. So that is like, the building blocks of reality. So what is the other stuff? Well, in quantum field theory, force is defined as an interaction between two of these building blocks. So, and whenever two of these building blocks, they interact, they exchange something known as a boson. That's why it's called a force carrier. It's always some force that's behind it. So this is the photon. It's responsible for the electromagnetic force. And you know electromagnetic force, right? Like, it's everywhere, in chemical bonds and stuff. And without this electromagnetic interaction, none of us would be here. No life would exist at all. And that is the gluon. So the gluon is responsible for the stability of the nucleus. So and it's responsible for this strong nuclear force. So without this force, again, we won't live, because nucleuses won't be able to be stable and everything will just decay very fast. And this is a W boson and Z boson. They're responsible for something known as the weak nuclear force. You can think of the weak nuclear force as the electromagnetic force that's very, very weak. And it's responsible for like radioactive decay. And yeah, that's kind of it. So yeah, these are the four fundamental forces in the universe. And as you can see, I mentioned the bosons of these three, right? Well, what about gravity? Sadly, we haven't discovered a gravity boson. It's called the graviton. And theorists propose that it should exist, and then it can incorporate gravity also in this standard model. But so far we haven't really found success. This is Paul Dirac. He was a British physicist in the 20s, and he was one of the main proponents of this quantum revolution. And essentially, he thought about, electricity at the very small scale. So like we know electricity at, our day-to-day life, from what we understand there, right? So he thought about, thinking about electricity at that quantum scale, at that subatomic scale. And this is another physicist, Erwin Schrödinger, who was also at the time of the 1920s. And you can see that the 1920s was a time where old ideas were challenged, new ideas come to life. So Schrödinger is mainly known for his thought experiment known as Schrödinger's cat. And what he thought was, if you put a cat in a box and there's some material, like some radioactive material, and if it decays, the cat will die. Now that radioactive substance has a 50% chance of decay. So after some time, you will think that the cat is dead or alive, right? Well, if you think in the terms of quantum mechanics, you will conclude that the cat is dead and alive. That it's in a superposition of, both things. So this is to show a very common quantum mechanical thing called quantum superposition, where a particle can exist in two states at the same time. And this is not theory. It's proven experimentally. Now this does not seem to make any sense whatsoever. How can something be there and there, right? Well, but it exists, and we really don't know why.
So, we talked about the two pillars, but now let's come to the theory of everything. How did this idea start? So, as you saw, those two theories, they clashed with each other. And they couldn't work well with each other, and we'll explain this next. And this can't be unified, both of them can't be unified, because first point, gravity is not like the other forces. As you saw, the four fundamental forces, there was no gravity particle. And everything in quantum field theory, it's mediated by particles. You have to define everything in terms of particles. So there's no gravity particle yet, so it doesn't agree with quantum field theory. And another thing is gravity is very weak, it's extremely weak. So suppose if you take a nail or any iron piece and put it on the ground, you can lift it up with a very small magnet. So that just shows how you can, take up the magnet with a very small magnet. So you're cancelling out the entire Earth's gravitational force with one small magnet. So that's how weak it is. And they both have a different understanding of space, as we said. So in general relativity, you saw that space is bent, and that's what Einstein thought. But in quantum field theory, space has to be, straight and no bends and stuff for it to work. So that's another point it doesn't agree on. And in the end, they both fail to explain, how extremely high density objects exist, like black holes. We've actually seen black holes, but they don't explain how. So if the current theories aren't matching up to anything, you can't find anything, not becoming the theory of everything, what do scientists do? They make a new theory. So this is the theory that became recently famous, the string theory. And if you think about it, it's completely out of our imagination. It's very superficial of sort, but yeah. This is Werner Heisenberg. He's one of the key proponents of string theory. So, how did he start? He thought of making a new theory by adding another layer of reality. As our particles are working, so he said, there must be something even below. So, he thought that everything was actually made of a bunch of strings. But by bunch of strings, does he mean this? No, he didn't mean that. He meant this. These strings, from his sense, was, loops of energy, extremely small, one-dimensional loops of energy. That's what he thought. So let's talk about these one-dimensional strings. These are one of the predictions of string theory. So that's how the name string theory came. So in one-dimensional strings, it's actually the particles that QFT describes, all those very small particles, they are instead replaced by strings. And these are oscillating strings. So as different oscillations on your guitar or any string instrument would give you different pitches, that way these different oscillations give different particles. That's what he thought. But sadly we have not seen these strings yet, and no prediction has been. So this is Theodore Kaluza. I know he looks a bit like an old Indian uncle, but he's actually German. So he thought of another concept of string theory, which is extra dimensions. So essentially it started by him thinking that, okay, Einstein says that gravity is caused due to folding of space-time, that is the three spatial dimensions and time. What bends to create the other forces? So he thought there must be more dimensions which are buried. And another thing was that the mathematics of string theory, it would only work out if there are more dimensions. So if we find strings, that would mean, that there are extremely small weird dimensions. Okay, so these dimensions, in fact, they're not like, right, left, like the spatial dimensions we experience. They're extremely small, they're curled up, and weird stuff happens in them. That's the... you can see that, we haven't found strings yet, we haven't found extra dimensions yet. Why do we still consider it as a candidate for the theory of everything? Well, first point is because, if you look around, there are some certain constants in nature that just exist. Like if you see the gravitational constant is there, which is just a certain number. So if you go anywhere in the universe, till what we've seen at least, that the same number will exist everywhere. Why? You don't know. It's just some random number. And also the speed of light in a vacuum, it's always a constant. So string theory tries to explain why these constants exist and why only these constants. Because even if they were a bit different, our universe would have been much different and everything would have been different. Probably none of us would have been here. And another thing is that, as you saw, gravity was one of the main problems with the two theories. So what string theory is trying to do is that it is trying to unify gravity. So if it's trying to unify gravity with all the three other forces, which would make it in one model and which would be good.
So Kian said that it hasn't been found an experiment yet, the existence of strings. Well, scientists are still trying to plow their way through, and they're trying to prove string theory through one of these two ways. And the first is through smashing particles. Like I said before, they smash protons, and a lot of energy is released by smashing of these particles. So what string theorists believe is that there could be one collision where some energy goes to one of those extra weird dimensions, and that directly points to string theory. So that would be a great win for string theorists. And the second is to recreate the conditions of the Big Bang. So string theorists believe that if we go back, if we can see what happens in the Big Bang, there's a possibility that early enough only strings existed. No particles existed then. Only strings existed independently. And if we can detect these strings, then again this proves string theory right. But some of you just may be wondering why do we need a theory of everything? Like what's the point of it all? Well, you may just be correct because we spend a lot of money, we spend billions of dollars on all these experiments. The Large Hadron Collider, which is in Switzerland, is worth $9 billion. And as of now, all the things that they detect has no application of any sort. So why do we do it? Well, I believe that it's our nature to know more. It's in us. It's curiosity. I mean, if they don't serve red chutney with uttapam, you'll wonder, ooh, why didn't they give this to us? And what is this? Okay. So that is in us. This want to know, this need to know, and it starts with asking questions. And that's how we get to what we already know. So, any questions? Yeah, same also.
So you talked about the cat thought experiment.
Yeah.
Now you mentioned there may be some practical thing. Can you suggest one or two areas where they...
Huh?
One or two areas where that duality exists?
As in?
Two states.
are there any practical situations in which that kind of duality exists?
This is an analogy. It's just a thought experiment to convey a very weird idea. Like as of now, we don't really have any practical application for that superposition, and it's just a analogy.
Then I can
Can
say
we give examples of quantum superposition? Yes, that's it.
Actually, there is. So, there's this upcoming field, it's called bio-quantum mechanics. It's very recent. And they've been trying to explain how the photons, say, I'm not sure about it, I just read about Bailey and nothing. You know what I'm talking about. It's about how when the photon hits a lead, so there's these things called reaction centers where they have to go and where the photosynthesis actually happens. Apparently, superposition does take place there because the photon seems to take multiple pathways to reach the reaction.
Yeah, there.
No.
Wait, first repeat the question.
So he asked, is string theory the only candidate for the theory of everything? It isn't, but it's the most famous one and it kind of appealed to us, so we wanted to talk about it. So there's another theory, another famous theory called loop quantum gravity, which also tries to offer an explanation, to the universe. If there are no more questions, we'd like to thank Arun sir and the AV squad. Oh.